Okay, welcome back. So I wanted to do a quick review from the chemistry module that we just did last week. And we're supposed to be identifying atoms based on the number of bonds that they can form. And of course, the way we figure that out is we have to figure out the number of valence electrons that they have. So our first one that we're supposed to be looking at is hydrogen. And hydrogen is atomic number 1, which means that inside the nucleus we have 1 proton. And outside the nucleus, we have 1 electron. So we have a little electron shell here. Actually, I'm going to make it more like that. And we've got our 1 electron there. And we know that this is not very happy configuration for this particular atom because it only has 1 electron in this outer shell. So this is its valence electron. And so it has 1 electron. It really wants, in this first shell, it really wants 2. And so this is going to be able to bond with one other thing because it needs to fulfill its valence shell. Now carbon is a little bit different. Carbon has atomic number 6, so it has a lot more protons and electrons. So if we were to put the protons in here, we would have 6 protons, and we know that because it's atomic number 6. And now we have 6 electrons that we have to distribute in the electron shells. So we know the first shell can only hold 2 electrons. So we have 2 electrons out of the 6 placed. We now have to add another shell outside, and in this shell we can put up to 8 electrons. But we only have 4 left. 6 minus 2 is 4. So we're going to put our 4 remaining electrons in there. And those are our valence electrons. Now it wants 8 because remember the octet rule says that in order for an atom to be happy, to be fulfilled, we need to fill the valence shell, and it only has 4. So we're going to need 4 more in here, which means carbon is able to form 4 bonds. Oxygen is our last one, and oxygen is atomic number 8. And so we're going to put our 8 protons in the nucleus, and then we have to start filling our shells. Our first shell, again, we're going to put our first 2 electrons in the first shell. We have 6 electrons left that we have to place, so we're going to sort of randomly put them out here in the second shell. 1, 2, 3, 4, 5, 6. So it's got 6 electrons, which means that it's not quite happy. It doesn't fulfill the octet rule. It really wants 2 more electrons to share with somebody else in order to be happy. So oxygen is going to be able to form 2 bonds because it wants to share 2 electrons. So we've got 2 bonds there, we've got 4 bonds here, we've got 1 bond there. So let's go take a look at our models. So now we have a molecule model kit that we use sometimes in class. And what we're supposed to be doing is we're supposed to be looking at these beads and figuring out which atom they represent. And in order to do that, again, we have to look and see how many bonds they can possibly form. So this little white one only has 1 hole. It can make 1 bond. So which of the things did we just talk about that can make 1 bond? This one here, if you look at it, it's got 2 places that we can hook on some type of bond to make 2 bonds. So you got to remember which one can make 2 bonds. And this one here, if you look at it carefully, it's got 1, 2, 3, 4 places to make bonds. And when we're, what's the word? When we're modeling bonds, sometimes we use these short little connectors. So like, for example, here, they can connect really close. And sometimes we have to use medium connectors, and sometimes we actually have to use long connectors. And this represents the fact that these guys have to kind of be closer to one another or further apart in order for models to work. And it actually works that way in chemistry as well, in that some of the bonds are longer than others. So over on this side of the bench, I built a couple of water molecules just to show you how the oxygen atom and the 2 hydrogen atoms are going to make this kind of bent shape. And remember, water is polar, And the reason it's polar is because there's unequal sharing of electrons. These guys are all sharing electrons, but oxygen is so electronegative, the electrons are going to be hanging out more often over here than they are over there. So this is going to be partially positive, this is going to be partially negative. Also, these guys have single bonds, right? They're only sharing one electron with this hydrogen and one electron with that hydrogen. When you get something like O2, so these are two molecules of oxygen, they're sharing two electrons. So each one of these bonds represents one electron being shared. Again, both of them need two electrons to fulfill their octet rule. And what we do is, instead of using like a short little white guy here that's short because they're close, we end up having to use quite a bit longer bond. At the same time, this, you can spin these around, right? This is moving. These guys, you can't really spin them around, and that is part of the downside of a double bond. Like, they're pretty stiff. This is going to come more into effect when we start talking about lipids and the stiffness of various different types of lipids. So you can see these are both O2 molecules, two atoms of oxygen. And the same thing applies when you have CO2. So carbon in the middle, it shares two electrons with this oxygen, and it shares two electrons with this oxygen. And instead of being bent like that in a polar configuration, this is pretty straight. Both of these are straight. There's no unequal sharing here in either one of these. So these would both be non-polar. Okay, so what we have here are three little water molecules, and we know that these are polar. We know that this end of the water molecule is slightly positively charged and this end is slightly negatively charged. And so what happens is, in solution, when these guys are all kind of hanging out together, you're going to have a situation where this part of this molecule is slightly attracted to that part of that molecule, just because this is positive and that's negative, and we know opposites attract. And then you might have something like this, where this end of that molecule is attracted to that end of that molecule. So they kind of like each other. They like to be near each other. And so this is why water has a certain cohesion. It's held together. And the sort of, we call it a bond, but it's not really a bond. The attraction between the slightly positive end and the slightly negative end of a polar molecule is called a hydrogen bond. It's called a hydrogen bond because you have to have hydrogen in it, and hydrogen has to be attached to something really electronegative like oxygen, nitrogen, or fluorine.